here to let you in on a secret. The secrets of witchcraft. This is Witchcraft Secrets from a Reverse Engineer. I'm Cafe Bet Alyssa Rosenzweig. Let's talk about the Magilectric Revolution, the most important thing of our time, the core of the modern life. And as you are all skilled mages, this is of course basic review for you. I don't know why I'm wasting your time on magic. But as you know, magic is, I've lost my cape. This is fine. Can just magic it out of existence onto the floor. As you know, magic is based on Star Swirl's first law, that magic can neither be created nor destroyed, only transformed. And this basic fundamental principle is responsible for everything we have in life, everything simple like levitation, or simple things that everybody likes to do, you know, to save Equestria, get to your fridge, teleportation, or I guess if you really want, 3D graphics. But there's another side to it. There is another side to Star Swirl's first law, because I said that magic can always be transformed. Can that mean it be transformed back? And in fact, yes, it can. There's another side to magic, a much more powerful form based on reverse-oriented magic folds. And this is known as reverse engineering or witchcraft. Witchcraft is spectacular. It's responsible for allowing us to take a spell and understand how it works, to modify it to our content, to share it with other mages. Yes, witchcraft is at the heart of open sorcery. So let's talk about how it works. There are a number of steps to basic witchcraft. For a simple problem, you might have something like the following. You might cast a spell, and then just make one teensy change to it and cast it again. And after each time you cast it, you're going to look at the resulting magic aura. And the idea is that if you take the two magic auras with the tiny change in the middle, you can figure out what's the only subtle change between them is. And if there's only one small change, well, then you're done. You found exactly what the change is. And if you keep doing this with lots of little changes, you're able to build up all of the parts of the spell until you understand exactly how it works. And you can cast it yourself with, you know, free and open sorcery. But for the more complex case, let's talk about our spelling convention. Let's talk about a spell F that transforms a magic object X into a magic object Y, denoted F of X equals Y, which is notation should be familiar to all of you from Math and Magic. Also, very critical to our spelling convention, as we are a multinational witchcraft community, is that color is spelled with a C. So let's talk about the steps. For a much more complex case, when you make a change to the spell, but all of a sudden, so many other things change instead, and you're just overwhelmed. You change one tiny bit in your input spell, and all sorts of things are changing. Well, what do? You cast many spells with many different changes, with many different inputs. For instance, if you're trying to reverse a spell that transforms this microphone into a fruit, I might first cast it, turning into an apple, then into a different type of apple. You know, first is a Fuji apple, then it's a Granny Smith apple, and, you know, go through all the different types of apples and look at all the magic auras, right? You know, that's what you do if you're trying to get an apple. And in each case, you record your results to make your table. But how do you actually do that? Well, this is where tracing comes in. For some spells, this is easy. For certain simple spells, for instance, a spell that would transfigure one file format into another, you know, you have it right there. There's no tracing needed. But for complex 3D graphic spells, you need to use a bit of magic ingenuity of your own in order to even trace the magic aura. So let's look at how these proprietary magic spells work. In this case, you have a blob, you know, and you have the kernel, and the blob is casting spells at the kernel is casting spells at the blob. How are they casting these spells? Well, it's going through a very special magic medium, the IOCTL medium. This is one of those these arcane acronyms we found in the tablets from thousands of years ago when other species populated this planet. We're not sure what it stands for, but we do know what it is and how it works. This is a magic medium. And the idea is that any spell the blob casts will go through this IOCTL and to the kernel, and the kernel will respond to the same magic channel, which means all of the magic auras we're looking for is going through this. So if we don't have access to it, we can't trace the auras. So what do? We use our own magic. We create our own wrapping spell that sits between the blob and the kernel and intercepts all of these IOCTLs, these MMAPs, these OPENs. Again, we're not sure what these arcane acronyms are. If anybody would like to tell me after the talk, I would love to hear, but we intercept them, and we do this with a dynamically loaded magic library, which we inject with LD preload, and this will enable us to intercept these system calls, and then at this point, we are the magic medium, and we can trace anything going between it. For instance, we can cast the Olvido spell, which is important for looking at a person's or pony's or process's memory. So, a memory spell, simple stuff. Might be prescribed, but that's okay. And so from here, we're able to trace the magic auras, and here onto the fun part of the talk. Actually doing the witchcraft. Because so far, everything I've said so far is just about collecting all these auras, collecting it into a table. And that's fine, but it doesn't actually do anything yet. Our question would be to deduce this function f that converts this magic object via the spell into the other magic object. So let's think about all the different techniques you might do it. The first technique is by far the simplest and works 20% of the time. This is the waiting technique, which involves cursing an IRC and waiting for divine inspiration. Highly recommended. Next one is the law of parsimony, otherwise known as Occam's razor. And this is the idea that simple f is more likely than a complex f. And so the reason for this is simple. If the blob has to calculate this f function, that means the hardware is using the value. It means the hardware has to calculate the f inverse, the counterspell. And that means if the f inverse is very complicated to calculate, that uses a lot of magic mana, which is expensive, and that's just, you don't want to do that, right? Especially for embedded magic, kind of embedded into the fabric of our society, or a laptop, either way. And you do have to keep in mind, though, this is things that are simple for the hardware, not necessarily simple for you. There are certainly functions that look simple, but if you actually think about how would you implement this in hardware, it would end up using a huge number of gates, which means it's unlikely because lots of gates means lots of power, means lots of mana. So that's the first technique. Next thing you want to do is actually look at this table and try to figure out what kinds of properties does the table have, and what could that tell us about the actual f? For instance, are there any special alignments to it? If it's a spell that transforms a number into another number, what about all the resulting numbers? Are they all even or all odd, or maybe they're all aligned to 16 or 64? Those are things you really want to pay attention to, because even if you don't know why that number is significant, it will be significant if there is such an alignment. And if there's not, that's also something that you want to pay attention to. If it's always aligned to 16, that might turn out to be the size of a tile. If it's always aligned to 64, that might be the size of a cache line. These are just numbers to keep in mind, depending on your hardware. The next property you might want to think about is monotonicity. For instance, with one of these number spells, if you increase your input number x and it's always increasing or always decreasing your output y, that's something to keep in mind. And that gives you a little sense about the shape of the spell and what it might be doing, how it might work, and it constrains you. If it doesn't do that, well, sorry, on to the next point. Maybe it's a spell you recognize. And sometimes in these complex spells, they're just built up of smaller spells, and some of those smaller spells are things you've been studying, like a linear spell, or, sorry, I forgot you guys are graphics people, and an affine spell. Happy? Or maybe one that's almost linear. These are things you recognize. You've been studying them all through magic school since magic kindergarten. You're used to that. So if that's the case, you got lucky. It won't usually be the case, but keep it in mind. You can take what you can get. On a much more different note, instead of these classic mathematical spells, sometimes you have ones that are interesting based on the bitwise representation. Because when you're working in hardware, everything is in terms of binary, which is why we call many of these spells hexes. So you want to look at, for instance, are there bitwise complements at play? If there is a notion of inverting the input, there is going to be a notion of inverting the output. And often that notion will exactly be this bitwise complement. So as an example, if you have a spell that turns lights on, and that corresponds to the number 7, and then you cast another spell to turn the lights off, and that corresponds to 8, well, that might tell you that is a 4-bit field, because 7 plus 8 is 15, and that's, F if you can't count. On the same note, you want to look at powers of 2, because these are very special in binary, both in the input and the output. If the alignment is aligned to a power of 2, that's often the case, and that's something you want to keep in mind. But also in your inputs, you want to look at the inputs at special powers of 2, because often when you have special inputs, F behaves in special ways. So if you're just looking at 1, 2, 3, 4 in that order, you may not understand what's going on. If you look at 2, 4, 8, 16, it might be a lot simpler, or might be a lot more complex, but just things to keep in mind. Next property is going to be based on entropy. And this is the idea that if you compare the amount of entropy in your input X and the entropy in the output Y, this will tell you a lot. And in practice, this means looking at just the number of bits in each if you're looking at binary. And conceptually, if they're equal, well, all you've done is just shuffled things around. If you're, for the mathematicians in the audience, you might have a bijection, or I don't know, I've been taking too much algebra. I try to stick to magic. But if you have more bits in the input than in the output, either one of two things is the case. Either the transform is lossy, your spell is losing information, which means if the hardware needed the original information, you have to look somewhere else for the rest of it, or exactly that, you are only looking at part of the output and you need to look a little broader. Conversely, if there's more in the output, then your input might be incomplete and you need to look for more broadly. It's possible it's just an extra padding, or they're just having extra stuff. But again, because simple F are more likely than complex F, it's just unlikely that you would just have these bits that are just not being used for anything. So, or sometimes you do. Win some, you lose some. Hey. Another technique, if you're visual, is looking at the graph. Again, this is especially helpful when you have some of these, near linears, what I was talking about here. In this case, you have constant slopes and a nice line, except there's other parts where the slope changes and, I don't know, it has some kind of linear staircase. How do you deal with this? Well, you might take a little discrete calculus technique, which is the fancy term for addition and subtraction. It can be easier to model the derivatives of your table, and just in terms of backwards differencing. If you notice that the numbers are, for instance, in that case, for this almost linear function, the derivatives would have just been all constant with some jumps, like a little square wave. And that'll be easier to find your f prime for than you can always just find f again, because, discrete integration, fancy addition. But pulling up to a much more broad notion, what about the different classes of f you can look at? You just want to think about what kinds of functions could possibly satisfy the properties. If you found that it's always aligned to 64 and that there's a notion of bitwise complements, it's probably not going to be some algebraic function. It's going to be some bitwise manipulation. If you found that every time you increase it, it increases by 2, that's more likely to be some sort of nice algebraic expression. If it's something else entirely, maybe you need to think outside the box even more. And just knowing the kind of class of function you're looking for can help you figure out how to at least narrow your search space. Because the problem is essentially, when you don't know anything about the problem ahead of time, you have an essentially infinite search space. But if you can find these properties, you can figure out the class of function. This will allow you to narrow it to something that you can actually start trying by trial and error. Intuition helps here, looking at the properties helps here. some combination of the two. When in doubt, witchcraft. Even, how do you figure this out? Well, another part is that there's this notion of purpose. Everything in the spell has a reason to be there. Nobody just casts a spell for no reason, unless the reason's like, your teacher said you had to and it's for homework, but which happens a lot in magic school. But in a complex spell, there's a reason to cast everything. It costs power, it costs mana to cast spells for no reason. So your job is really to figure out what the reason is, why we're casting it. So one thing you might look at, how about this example? What if you have this texture descriptor? You have a field for size, then some unknown field, and then a field for depth. Anyone want to venture a guess what that unknown field might be? This is from a very complex example. Only the best. Anyone? Wow, height. I wonder what. Yeah, exactly. This is a Molly Midgard texture descriptor. This is a very simple example of something that comes up all the time. This idea of these proximate fields having these proximate purposes. There's no inherent, nature of the universe reason it has to be like this. But in practice, you're a mage, and things that are simple to you as a mage are also simple to whoever designed the spell in the first place, who was also a mage. And if you like putting your width and height, your depth together, chances are whoever originally wrote the spell likes putting your width and depth. Anyway, info drops. My favorite slide. When in doubt, instead of trying to figure out the answer, have someone else tell you the answer, because it's everywhere. Conference slides like this one. The vendor blogs. People can be really closed up until all of a sudden they have a chance to talk about, their secret sauce. Oh wait, that's kind of what I'm doing here. Never mind. Talk canceled. Code drops, the kernel. Even when you have a proprietary user space, the GPL means that you still have this open source kernel space until you don't, but we don't talk about those chips. Which means even if you don't have a lot of information, you do have a little bit just from reading the kernel driver. So for the graphics chips, it's not good code necessarily, but it's usually legible, usually. And so this can just tell you things. And even if it doesn't tell you exactly this field corresponds to this value, it can at least give you hints that, oh, this hardware supports this feature, and maybe we should figure out where that feature comes in. And you want to know your search space, because then you go from being uncountably infinite to, countably infinite, which is, my teacher says that's better. It's still infinite, though, so, I still cry at the end of a Friday, but Google's your friend. There's I don't know how that slide got here. Tomeo, did you add this? I don't know what this was about. It must have been one of the coworkers. I don't know what the XDC hallway track is. I don't know how you could possibly learn anything about other vendors' hardware from talking to people in the hallway. I don't know why we have hallways. That seems really silly. You just a thing you talk about, install, and just cast the spell so nobody knows what I was. Anyway, if all else fails, you can just move on. The fact is that these complex spells means that there is no shortage of things to reverse engineer. If you can always circle back to things. There's a time and place for every part of the spell that you're trying to reverse. So it's always nice to get it on the first try, but you don't have to. So that just takes the pressure off, I guess. So let's go to an example. How about this assembly from the Molly Magic Guard architecture? You have a simple shader, which just discards a pixel based on a condition, and it compiles to this condition and a discard. And this is just some simple assembly, right? What if you try having multiple conditions together? You look for condition A and condition B, and you AND them together, and then you try to discard based on that. What you would guess would happen is that you would compute both conditions, and then you would have an instruction to AND them together, and then finally feed that into the condition, the discard. But what actually happens is that there's no AND instruction. you have these two conditions magically being written to the same register, the same exact register, with nothing consuming them in between. And there's nothing to combine them. Oh, and now there's a magic number ingested in the branch all of a sudden. So what's going on here? Already, we have some idea of the purpose of this mysterious 8888 number. We know that it must somehow be telling the hardware that it should take these two conditions and AND them together. We don't know why those bits mean that, but we know that that's conceptually, right? So the next thing we might try is, again, casting lots of other spells. Instead of ANDing it together, what if we tried ORing it together? Now it's a different magic number. NAND, different one. NOR, different one. We can take all these spells and cast it into a table, and we see a problem here already. Yes, the encoding is unique, but we have this question of entropy, because there's only 4 possible ways to combine these two conditions, which means there's 2 bits of entropy on the left. But this is a 16-bit magic number, which means there's 16 bits of entropy on the right. What happened to the other 14 bits? Why would they just disappear all of a sudden? And we're seeing all these repetitions, and like, this is weird. And we could stop here and be satisfied with this, and maybe we might be satisfied if we're on a time crunch. But we want to figure out what else could that code be doing. Maybe we need to try something more broad. So you might this is usually where you go back to step 1 of the reverse engineering process, course in IRC. But you might try eventually, after banging your head against the wall for a few hours, putting a 3rd condition in there, doing 3 conditions altogether. And we see the same exact pattern, but now there's a new magic number, this 8080. And this is significant because we're no longer repeating every single nibble. Now it's repeating bytes. And so this tells us we're on the right track. So what if instead of doing 3, we did 4, another magic number, 5. Okay, 5 is where it breaks. 5, now we see an actual AND instruction, which means we've already learned something already, is that there's a limit of only 4 of these conditions that you can combine at once. So now we can figure out exactly what the purpose of the field is that it allows us to combine 4 different conditions into 1 condition, and it specifies how to do that. Okay, how does it actually do that, though? Well, we can think about the sort of space of this function. Each of these 4 conditions can be either true or false, which means they are each 1 bit. So you have 4 bits in the input, which means with 1 bit in the output for the Boolean output, it'll take exactly 16 bits to represent every possible function f just as a map. And what do you know? The magic number is exactly 16 bits, which means we've solved our sort of entropy issue, because now we have exactly the right amount of input for the amount of output we have. But it doesn't tell us how it works. So let's go back to our table. This is usually when you start looking for divine inspiration. You just kind of stare at this, try to let the numbers seep into your soul, if you have a soul. But you might try rearranging it, and you notice something interesting, is that there is this notion of taking complements of the expressions. You have and NAND, or and NOR, and on the right with the codes, you have the same thing, these complements, with bitwise knots. And you can see this clearly. If you OR them together, you get all 1s. And so that's something. This tells us that this is a bitwise type representation. And so this is something, this seems important. It doesn't solve the whole problem yet, but it gets us there. And furthermore, what if we looked at this last one, where we have this all 4 ANDed together? If you think about the truth table of having AND with 4 inputs, it's always 0, except for the last case, when they're all 1, in which case you have a 1. But then look at the code. That's 8000. That is, in binary, it's always 0, except for a 1 at the end. And with that, we figure out exactly what this is. It's not a function. This isn't source code. It's not sorcery either. It's just this truth table for the conditions, which means what we have is exactly, well, any takers? It's a lookup table. Thank you. Any questions? Before I wipe your minds. Anything?
One thing I will probably ask is, do you encounter like hardware bugs when you try to do reverse engineering? And when you see that, what would you do?
No.
I don't believe that. I don't believe that answer, but there probably is some bugs you probably encounter sometimes.
Kernel code drops in the hallway track, neither of them exist. Anyone else? Well, if that's it, it was great to be able to share this with you, but as I said, I'm strictly forbidden from being here, and you're strictly forbidden from knowing the contents of these slides. I kind of may have stolen some of the information from my teachers at Witchcraft school, the school that doesn't exist. Yeah. Needless to say, I will have to cast a memory spell for you as per the terms of the non-existent disclosure agreement. So with that, olvidare!